I think we've got a midterm due, and I guess it's due tonight. But don't worry, you got plenty of time. I think everybody should submit at 11:59 p.m. and then we'll see what happens with Blackboard, because that's the best thing. Just wait till the last minute. Just kidding. If you could all submit early and submit often, that'd be terrific. It looks like there's already been 56 attempts at this thing. So somebody's submitting, or a few people are submitting. Are there any questions about the midterm that you'd like me to try and cover? Can you guys hear me okay? Here, can you hear me? Oh, good. Oh, good. Okay, I figured somebody had to have questions about this midterm. If not, then I will proceed to go through new materials. So, hearing no questions, sounds like you guys are up to speed, which is good. So I'm going to close out the midterm. I had it opened with this anticipation that you guys would have questions. Closing it out. Going once, going twice, 3 times. And it's gone. All right then. Let's move on to the next assignment, which is covering homework. Which homework is next? 8 on flip-flops. So we were starting to cover that in our last exciting digital design class. And one of the things that we have here is a simulation of the internals of a 555 timer. And what I did was, I don't know if this is going to show very nicely. You know, the thing to do here, let's see if I can do this. Turn off the backlight so you can see. Ah, that's better. That's better. So what I did was this is my little homebrew thing. I got a thing called press and peel, and I run it through the laser printer, and then I run it through an iron set to cotton, and it transfers the toner onto the copper. And I take the copper with the toner on it, and I drop it into some ferric chloride, which etches away the unneeded copper, and it leaves behind the traces. Then I have the very fun time of drilling holes, and then I mount my own little printed circuit board. I can chug out a printed circuit board like this in about 45 minutes, which is kind of long, I guess, but it takes weeks to order them from places like China. So I figure, especially if they get stuck in the Suez Canal or something awful like that. So I figured I'd make my own. There's a 555 timer. Here's a little capacitor. And what this does is it charges until it gets to a threshold, and then it trips an RS latch and causes it to reset by discharging the capacitor. And that capacitance resistance circuit, it causes you to create a bistable multivibrator. Bistable means 2 states, and multivibrator because it vibrates between the 2 states. And so what you do, see if I can get this to work, is there, it's working. There it is. You can specify what the time constant is, and then you can build your own little square wave generator. And that's a little LED that I've got going here. And you can make the duty cycles very long on this or very short. And this, if you look at the book, I don't know if you guys like to sort of look at the book, you can see the RC circuits that are involved. And what's interesting about that stuff is it's a fairly well characterized integrated circuit that has, let's see if we can get this under the camera. Let's see if we can do this. Yeah, there you go. It's a little bit out of focus. I wonder if this thing is going to focus for me. It doesn't look like it is. For some reason it's not focusing. But what they do is they give you the duty cycle up in here as a formula, and they give you the clock frequency over here based on a couple of resistors and a capacitor. And they tell you what the clock period time is. So what I'll do here is let's go back. Let's see if we can do this. And alrighty. So now that you've seen that very impressive demo, what we'll do is we'll talk a little bit about duty cycle. So what you want to do is take the amount of time that you're on and the amount of time that you're off. Right, so this is the time on. This is the time off. Right. And your duty cycle is expressed as a percentage of the time on divided by time on plus total time, so that's time off. And then you multiply by 100, and you get duty cycle as a percentage. And that's the duty cycle thing that allows you to adjust how much time something is on versus how much it's off. And you know, this is an interesting thing, because if you have a device that you need to take a measurement, maybe it takes a measurement once every minute, maybe it takes a measurement once every week. So if you're trying to measure, let's say, how much oil is left in your oil tank, your device might only need to turn on once a week, and during the rest of the time it could harvest energy from parasitic RF emissions, let's say from a local radio station. Charge itself up, and then a week goes by, and all it has to do is turn on for 20 seconds once a week. And so it doesn't need very much energy to turn on for 20 seconds once a week, and you can continue that indefinitely for your little sensor. And so that's kind of an interesting idea, and in fact you could make products out of it. Speaking of products, the 555 timer chip, which is on this little circuit board over here, I'll show it to you again just so you can see that little guy. I don't know if you can see it. It's hard to see. Can I hold it up? Yeah, you can see it all right now. That little chip is one of the most popular chips. Really, people just really needed these little timers, and they sold a lot of these chips, and they still do. And we've got a bunch of them in the lab, so you can use them. It is possible, I think, for us to switch the sharing. Let me see if I can do this. Stop share. And then I'm going to try and share again. Share screen, and this time we'll share the desktop. And now you can see here is a list of things that you can watch, and one of them is a simulation of the master slave flip-flops and a 555 timer. Here's the internals of the 555 timer. Let's see if we can show that. So what we'll do is we'll hit play, and now you can see this is a cross-coupled NOR gate, so that's an SR latch. This here is a couple of comparators. So these are op amps that are set up to output a 1 or a 0 depending upon whether you're above or below a threshold voltage. That causes this to set or reset. And you can see down in here, the set or reset is essentially squaring off what is an analog input voltage that's coming from charging and then discharging this little capacitor over here on the left. So what he's doing is, you can see the discharge occurs whenever this transistor gets a little current into his base. And that causes the capacitor to discharge through and goes through this little transistor and then goes through ground. So all we're doing is charging and discharging this little capacitor through these two resistors. And that's how we're able to get this oscillator to work. And everything in the dotted line, that's what's on the chip. So what's on the chip is two comparators, a couple of NOR gates, and a transistor, and various resistors, and that's it. What you have to add when you use one of these things is a resistor and a capacitor, and maybe two resistors in this case. And that's it. So that's kind of a cool little chip to have handy, and it gives you an opportunity, I think, to kind of I don't know, get a square wave with an arbitrary frequency. Here's another one where we got a master-slave flip-flop simulation. So now this is cool too, and you'll like this. This is the cross-coupled NAND gates, which we saw from before. That's the latch. And then what it has is these two NAND gates. Now if you're looking over here, they each have a leg which are tied together, and they go into a clock. So during the rising edge, this is going to see a 0. During the falling edge, it'll take what is feeding these NAND gates and gate it through. So the NAND gates will gate nothing through until the clock pulse is associated with a high pulse on this end. And there's an inverter there. So at the high end, when the clock is high, this is low. When the clock is high, it now gates the J and K inputs to these NAND gates so that they can see their inputs. They're now sensitive to changes on input. And then what they'll do is they'll input to this latch. So this latch has now got a something stored into it. Perhaps the J is asserted and the K is not. And then what will happen is when this clock falls, these NAND gates will no longer pass the input into this latch. And so as it falls, this side of the inverter will go high, and then these two NAND gates will take the output of those two NAND gates and run it into these two NAND gates. That is called a master, and this here is called a slave. And what you have done with this clock, when you design in this way, is you've created a master-slave flip-flop, which is going to trigger on the falling edge of your clock. And so that means that you have a fully synchronous system, and you can watch this thing in action here.
Just wanted to give you a brief
rundown. Now here's your SR latch.
Do an analysis on the
set is S and R is reset.
This is
and this is called a multi-stable, multi-vibrator, or bistable actually. Bistable because it has two states.
Inputs to the NAND gates are asserted high. That's never supposed to happen. Once you have a race condition like this, things can go south pretty quickly with your SR latch.
So don't set both sides high at once with a latch like this. You can do it with JK flip-flop, but not a latch.
And they also use master-slave relationships. So let's take a look at some other mechanisms for screening.
So now we've got a clock coming in. No master-slave, just one clock, and so it's going to level trigger the inputs, and so it'll see those inputs as long as the clock is high. And so this gives us a way to kind of protect the inputs a little bit using a clock being strobe, so we could change things around when the clock is low.
More reliable when you go to sequential circuits. There's a thing called the master-slave flip-flop. So instead of using two NAND gates to screen out the clock, what we'll use is one flip-flop.
Now you can see it in action.
The inputs.
And now you can see the clock is strobing back and forth in through here, allowing the
clock, which can strobe
this is a D master-slave flip-flop to trigger on an edge.
Got a clock that's out of phase with
the input's always high here, but once you change it, it should propagate to low eventually, so it'll take two clock cycles to do it.
Clocks coming in. This one comes in on the high signal, this one comes in on the low signal, and that's called the master-slave relationship with a single clock input and a single control input. This is the...
now you can see it's going to switch. So it's going to switch from high to low.
Input changing, and now we can see it.
And it's high. Now it switches one from high to the other.
Propagates.
One's high, the other's low.
It takes a clock pulse going up and then down before it propagates through.
So now you can see master-slave flip-flops
let's try another one. We'll go and do a sequential logic flip-flop called the edge-triggered D flip-flop. So here's the edge coming in. we only want to trigger on the edge because that ostensibly makes the flip-flop a little bit more reliable. And so now we'll...
The goal is not to
change the
sample
state.
when the inputs are changing. So we have to be very specific about when we sample. In this configuration, we're only sampling on an edge
to do it.
of the clock.
And here we can see the state change occurs at the bottom when the clock transitions up.
So this goes on and
So
on.
that's kind of an interesting way to make things a little bit more reliable in edge.
You can play with those things directly. And I think what I'll do is I'll stop the share and switch now back to the camera. Let's see if I can get this to work. Screen share, visualizer. And presumably you can see the screen now. So that's a that's kind of a cool thing that you're able to simulate these guys with free software, and you can watch the videos on how all that works. And that helps, I think, with the conceptualization of how these flip-flops work. Let me see if I can get you back to the homework assignment. So that's homework number 8. Okay. So now you've seen JK flip-flops in action, master-slave flip-flops in action. Let's see what else we need to know. Alright, so one thing we can say about master-slave flip-flops, now that we've seen them, master-slave flip-flops have one latch, where a latch is defined as cross-coupled NAND gates or NOR gates, doesn't really matter. Right, so that's what a latch looks like. And then here's the input. Here's the output. And then if you wanted to insert some sort of another latch, the outputs Q and Q prime would be gated by, let's just use a couple of NAND gates here. And then here the inputs are gated by a clock, and then this would be the S and this would be the R. And now it's pretty clear. During the positive clock pulse, S and R are able to get through, and then during the negative clock pulse, this output from the SR latch will be able to get through to the, this is the master, and this is the slave. And that is an MS SR latch, master-slave SR latch. And now we've got, an opportunity to see what it is we can do in order to be able to create various kinds of latches. In fact, one thing you can do, if you recall, is you can convert one latch into another latch, and we did a nice exercise last time to show how that can work. If, for example, you took this and ran it like that, that would give you a D flip-flop. Right, because you converted the SR master-slave latch into a master-slave D flip-flop. Similarly, if you took that out and you put these two things together, that would be a T flip-flop. So that would be a master-slave T flip-flop. And if you just had this going in through here, that would be a clocked RS latch. Yes? I've been using uppercase in the lectures, I think. It's always uppercase, as far as I know. But if I write D and it's lowercase, it's probably just because I slipped in a digit or something. So that's you know, that's probably me making a. There's no difference. It's just a typo. Just a typo. Just a typo. Yeah. So I mean, here's the thing. If you see something like this, and this is question number 4, right? Here's question 4. So question 4 shows, I don't know. So this is this is J. This is supposed to be K prime. This is Q. This is supposed to be Q prime. And now what we want to do is figure out, you know, what is D equal to. It's pretty clear from this that what we've done is we've got a JK flip. Well, we've got a JK flip flop starting with a D flip flop, and so you could look down the list and you could see that right away. And also, if you wanted, you could say D equals, and you could write this out, JQ prime or K prime Q. And so that comes directly from an inspection of this this circuit here. Is this in focus for you guys? This doesn't look in focus to me. Yeah, I thought so too. Not good. Let's see if we can focus this. I don't know how. Well, here's something called manual focus. That looks better to me. Yeah, something's going on here with the autofocus. It's not right. And then you guys said something. Well, maybe I wonder if I can change the exposure a little bit. This is new software for the camera, so I'm still experimenting. So you found something about autofocus here, or what was it? Auto contrast? I don't see that. Oh, sharpness. Oh, that's better. Yeah, it seems dark to me. I don't know why. Weird, right? Because this is a light board shining from the back, and it should be a nice contrasty image, but I don't see that here. But at least it's a little sharper. Yeah, very peculiar. So I may go back to the other software. They said don't use it because it's old, and I'm like, well, okay, but it worked good. So let's see. Do you have any questions about this homework 8? Could you? Oh, this is question 4, right? So this here is looking like a JK flip-flop starting with a D flip-flop, right? So we turned a D flip-flop into a JK. So it's called The answer is D flip-flop starting with JK. No, wait, which one is this for? It's JK flip-flop starting with D. And it's pretty obvious, right? You started with this, and you ended up with that. And at the end of the day, it looks like JK with a D inside. And that's that. And let's see what else we got here. Yeah, this is just a bunch of flip-flop conversion questions. Question 7 asks, a master-slave flip-flop behaves similarly to a clocked latch, except that the latch's output can change only near the rising edge of the clock. Well, that's false. A master-slave flip-flop behaves similarly to a clocked latch, except that the latch's output can change near the rising edge of the clock. Is false because a clocked latch output can change when the input changes and the clock is high. So if we look at something like, like this section right in here, just because you've got a clock coming in here, since it's not a master-slave, when the clock is high, you're vulnerable to changes on the input. So you want those inputs to be stable. You want them to be guaranteed to be stable when the clock pulse is on. But if they're not, then this entire window of time is subject to changes on input. So now S and R could theoretically change while the clock pulse is on. So if you're dealing with master-slave relationships, you want to try and see if you can make that more reliable by clocking on a rising edge and then clocking on a falling edge. Let's see if we got any other questions. Number 1. Yeah, so that was the one I was doing just now. We were doing the conversion from this is on the one side the latch, which is equivalent to right. So when you see these two cross-coupled NOR gates, that's the latch. With the inverters coming in, you're basically taking a NAND gate and converting it into an AND gate. So I just wrote the AND gates in here. And then this is another cross-coupled NOR gate right in through here. And so this is acting as a master and then a slave. You see? Does that sort of make sense? Yeah, so what you want to do, maybe you can watch the video. Let's see if we can play that. So this was the, I'll see if I can do this, stop share, and then we're going to do a start share. And now we're back to the desktop. And so now here we have the video that's associated with that question. So that's a cross-coupled NAND gates instead of NOR gates. And other than that, it's the same sort of thing. Let me see if I can play this again.
Just wanted to give you a brief thing.
I'm going to zip through this section here.
But it takes a clock pulse.
So there's
going up and
so
then
there's
down
the D with the master slave.
Through. But this one's being used.
Here's the edge detection, which we saw from before.
As well as the and another flip-flop.
Now we've got the JK.
And the difference between this and the level-triggered D flip-flop is that we're using 3 input AND gates.
So
AND
you got
gates
J
here,
and K coming
on
in.
the input, and the third input is for the J and the K, and that should make things rather more reliable. With both
Let's see if I can zip through this.
a reliable flip 4-gate delay, 3 or 4 gate delay simulator itself is maintained at a specific frequency.
What I think would
and
be
is,
fun is if we went to
adjusted
the
by the resistor and capacitor
Valstead.com
according to a
guys
formula that's
and try to
supplied
do our own little
with
circuit
the
simulation.
5x5 timer.
So let's do that.
And there's some diagrams in the book that show you.
I haven't been there in a while. But I think there's a yeah, I can't tell. Let's just do this. Start a new screen. I thought there was a link in there. We'll go to Valstead. Oh, learn to type. Valstead circuit simulators. Oh, it's an applet. May not work. Oh, it's working. So let's see what we got here. We should be able to find flip-flops. There we are. And so now you can find all the flip-flops that are in that homework. So here's the SR flip-flop from before. And let's see what else we got. Here's the JK flip-flop now. They're both high, which means it's set up to toggle. If I make this low, then it's just going to go into the set, and it'll stay set. If I make it both low, it'll hold. If I make K high, it'll reset. And if I make them both high, it turns into a toggle flip-flop. And then you can see how the toggle flip-flop propagates from the master to the slave. He's not showing you the clock pulse down here. I don't know why. It might be a good way to do this. Just a minute. See if I can move it. Oh, there it is. I gotta move my screen. That's the answer to that one. So you can see the output in here is constantly changing. But when it does its change, it's on a falling clock edge. Even though it samples the master at the rising clock edge, it doesn't propagate to the output until the falling clock edge. Just kind of interesting. So that's that. You've got an opportunity here to try a few different things. Here's a yeah, there you go. Now we've got the simulation here for the 555 timer. And what you could do, if you wanted, I think, is you can stop the simulation. But the question is, can you change anything? Yeah, he's... Select drag. I'd like to be able to change this. He's not letting me. Seems like there should be a way to do that. But I don't see it. Maybe it's just stuck. So that's a low duty cycle oscillator. Let's run that and see what happens. So here you can see the low duty cycle is such that his on time is much smaller than the off time. So that's kind of interesting. We could probably speed that simulation up. Or not. I like watching it march by. I think that's more educational. Here's using a diode. Let's see what else we got. Have we seen any transistor simulations before? I think we haven't. That might be interesting too. So here's a transistor, and what we're doing is we're showing the current going into the base. It's a very small current in microamperes, and it's being used to gate a rather large current. But there is some small voltage drop across the barrier, and so the voltage drop itself has caused some change in power. Let's see if we can change the base voltage. There. So you need a certain amount of voltage to get current to flow into the base. So it's an amplifier. And the more voltage that goes in, the more current will flow. So that's cool. That's what transistors do. It's what tubes do as well. I don't know if this thing has tubes. Yes, it does. Here's a triode. So now what we can do is we can change the grid voltage. If you take the grid voltage down, the amount of voltage that flows, the amount of current that flows is reduced. So here it is down to 5 microamperes. And check out the bias here. This is a 500 volt plate. And now what we'll do is we'll increase the amount of current into the grid. Well, let's say, the amount of voltage into the grid. And now we've got a way to get voltage to go through. So this works just like a transistor, only it's huge and emits a lot of heat, and it's got a glass envelope and runs in a vacuum. Now if I reduce the plate voltage, that has a similar effect to reducing the grid. You want a high plate voltage bias there. So that's kind of cool. And it's neat that you can simulate both these things. So this is working just like the transistor. Only this ends up being a voltage variable resistor, and the transistor is a current control current source. Another kind of transistor might be the FET. That's a voltage variable resistor. What we can do here is reduce the voltage on the gate, and that will change how much current will flow. Isn't that cool? So now you got the real simulation of how the transistor is working. Nice animated simulation. So if you never take a course with transistors again, at least now you can say, oh yeah, I saw how that works. Transistors are just little amplifiers, which you can set up to work as switches as well. By the way, field effect transistors, they work like pinching a hose when the gate voltage is reduced, right? It's like you pinch the hose and the water can't flow through. Increase the gate voltage and you let go of the hose, and now the current can go through. So this is a voltage variable resistor, whereas the bipolar junction transistor is a current control current source. So that's sort of interesting, I think. So we did the flip-flops. I guess while we're here we could do counters, because we've been playing around with counters now. So here's a counter made with JK flip-flops, and you can see it's counting in binary. And we can now design counters that do just this sort of thing. He's counting, this is the least significant bit on the bottom here. So he's about to count to 16, then he rolls over to 0. And this is an up-down counter, so we can make it count down as well. And I could show you how to do the design on an up-down counter. So here it counts from 15 down to 0 and then starts again. So we can build a counter that does that. That's fun. And in fact, I think we did that last time. We were counting to 3 and then counting down from 3. But we didn't build an up-down counter. That we can do. So this is a counter that can count both ways. So that's cool. Let's see if we got anything else in here that's cool. Here's a Johnson counter. And you can see the high bit is just walking. This is a walking ring counter. That comes from Robert Johnson, who was the vice president of Burroughs. Patented this in the 50s. Also called it a twisted ring counter. Let's see. I don't want to do that now. Tunnel diodes we don't do. TTL. This is transistor logic, and this is what's inside the NAND gates for things like a 7400. So if you get a 7400, you'll have 4 quad, they call it quad NAND gates. That's 7400. Let's look at some other, yeah, there are variants, other logic families. You don't have to care about that right now. So we did the flip-flops, we did some counters. See what this shift register looks like. Well, there you go. This is cool. So now you can shift a bit in and watch as it flows from one register to the other. So this is serial to parallel conversion. If I want this to say 1010, I can go 1, 0, 1, 0. And you can see 1010. And then it gets scrolled out. So that's cool. If there was a step function, I would just go one step at a time, but I don't see a step function here. Let's see now, what else do we need? I think that covers it. I mean, there's a lot of interesting stuff. You should be encouraged to play around with this stuff. And, you know, things like the little static RAM, the ADD converters. This is a lot of fun. You know, a lot of fun with this thing. Let's see what else. I don't know if you've ever heard of the Joule thief. Joules, you know, they're power. And what the Joule thief does is it attempts to create a little buck boost regulator that will take a battery that's dying and give you enough power to run an LED, even though the battery could be almost nearly depleted. The LED can continue to work. So this is stealing the power out of the dry cell. And normally what happens after a dry cell, you know, goes below 1 volt is we throw it away, but there's still a lot of power left in it. So the Joule thief will suck the power out of it. It's kind of a nice idea, actually, if you think about it, because so many batteries are filling landfills, it's not very green. And they're filled with nasty chemicals. Really nasty stuff. Even worse is the LiPo batteries. That stuff, when you grind it up, they call it the black mass. It's very hard to extract the lithium out of it. And that's going to be a big deal once all those electric cars, well, effectively have gone surplus because their batteries have gone bad. And we can expect that soon. So here's the electromagnetic alternative to an SR latch. You don't need a transistor for this. You should be able to see, I think this coil is something that we can energize. Let's see if I can get this to work. There we go. So now this coil is being See, that's a little clapper. And he's being held by this electromagnet that's being energized. But if I interrupt the flow of electricity into that thing, right, what happens is the electromagnet loses its magnetism, the clapper goes the other way, and now energy flows through this coil and causes this clapper to close. Now if I interrupt the energy here, this clapper will return to its original set, and then the energy will flow through here, and then this clapper will close. Thus we have created a set-reset flip-flop out of a couple of relays. So you can do set, or you can do reset. Isn't that cool? So that's a sort of a, I will call it, way in which you can build computers without transistors at all. Just use relays. And that's how they used to do it. The original Zeus computers in World War II were all built with relays, and the Harvard Mark IV computer was built with relays. And many of the Bell Telephone Lab computers were built with relays. Let's see, where did that relay thing come from anyway? I thought it was in here somewhere. Doesn't matter. So that gives you a little bit of an idea of how you can simulate these things. I think that's very fun and very educational. Yeah, I don't know where the relays went. I know I had it, but I somehow mislaid it. Let's switch back to the camera. See, share screen, and there. Can you see the camera okay now? I guess you can see that. So let's see if we can't do a design. Let's do 0, 1, 2, 3. If the input is equal to 0, that's what we do. We count up. But what if the input is equal to 1? Let's pick a different color. Well, then what we have here is a finite state machine that has, it's more than just a counter. This is an up-down counter. An up-down counter has two modes. What we'll do is we'll write U/D. And then we'll write A and B. And we'll just number it like normal. And now, here's the interesting thing. We have two, this is the up, we have two modes, up count, we have another one called the down count. Right? So in the up count, next state, A plus B plus, 0, 1, 0, 1, 1, 0, 0. So it goes 0, 1, 2, 3, back to 0. That's fine. But what if we're counting down? Well, then from 0, when you're counting down, comes 3. Then when you're at 1, next one is going to be 0. Is that right? Yeah. So if you're in 3, you go 3, 2, 1. So here's 3, 2. When you're in 2, you go to 1. When you're in 1, you go to 0. And when you're in 0, you go to 3. So you can see these things are different behaviors, and I grouped the behaviors by the input into our little counter. So to build our little up-down counter, I now have to select a flip-flop implementation. So if I use T sub A and T sub B, then whenever there's a change, I have to put in a 1. Here there's a change. It looks like there's a change on both of these. Looks like there's a change on the least significant bit. And here both bits are changing. Here there's changes. There's a change here but not there. Looks like there's changes on both over here. And there's change in the least significant bit over there. So what did we notice? Well, T sub B is equal to 1. That's pretty cool. I mean, that's nice. It doesn't get better than that. What about T sub A? Well, for that one, I'll probably have to number my K-maps, right? 0, 1, 2, 3, 4, 5, 6, and 7. And then what we'll do is we'll attempt to get T sub A as a function of U, A, and B. And so we'll make a little 3-variable truth table. And then what we'll do is we'll read off what T sub A is supposed to be and set it equal to a minimum sum of products 1, 3, 4, and 6. Let's change colors to make it clear. All the rest are 0. Now I can loop here and I can loop there. And this one here is called U prime B. And this one here is called U B prime. And so now T sub A is equal to U prime B or U B prime. Well, prime. So now I can design my little up-down counter. T sub A, T sub B. Might as well go back to a pen now. And now I can have exclusive OR going to T sub A. That's an A. And I got 1 going into T sub B. Q sub A, Q sub A prime. B sub prime. I should just call it A and A prime. There. And now I've built my little, I've designed my little up-down counter. All I have to do is change U from 0 to 1, and this will change the direction in which it does its counting. Isn't that cool? And the answer is yes, Professor Lyon, that's cool. And what makes this different from a regular counter? Well, a regular counter visits each state once and only once. A finite state machine is a more general thing, and it can visit the state more than once for any given count. And because this can count backwards and forwards, this is truly a general finite state machine. Whereas a counter, which only does a count, continues to repeat the numbers indefinitely, that is a degenerate finite state machine, which we call a counter. So that's an interesting point, and now you've got an idea as to how to generalize this notion. Here's the input. We haven't seen that before. And we write the input along the arcs, just like that, in certain machines, and we can discuss that later. Any questions about this? So we've got ourselves a nice little example of an up-down counter. Cool, right? You need that stuff. Any other questions about homework number 8? I'm just scrolling through now to see if there's anything else I ought to be doing. Let's see. So here's one you might look at. 14. It says, for a D flip-flop, the next state is always equal to the input. Is that true? So if the input's a 1, the next state's going to be a 1. Use a little clock here if you like. Who wants to give that a try? Cool. What do you think? I'm doing question 14. For a D flip-flop, the next state is always equal to the D input. So, what do you think the next state equation is going to be for a D flip-flop? Alex, would you like to help Akul? Alex, are you there? How about Alexa? Would you like to help Akul or Alex? So, we're trying to figure out the next state equation for a D flip-flop. What does a D flip-flop do? Yes, it does. So the next state is going to be D. If you put a D on a D flip-flop, it just delays it by 1 clock cycle and then presents it to the next state. So the answer is true for 14. That is always true. So I'm getting a sense that maybe people are kind of not paying attention or something. I don't know. Let's try another one together. Let's try 15, right? For a D flip-flop, when the present state goes to 0, that is Q equals 0, and let's see, the present state is 0 and goes to the next state Q equals 1, so we went from 0 to 1, the required input for D must be D equals 1. In other words, to go from 0 to 1, the input must be a 1. Is that true or false? Anyone want to chime in on that? That is true. It's true because it just delays the input. So in other words, let's redesign now this little up-down counter. Only this time we're going to make a difference. And the difference is we're going to go to a D sub A, D sub B. Right? So now we know the input is going to look just like the next state. So what that means is I just take A plus and B plus and I rewrite it over here. And it goes 1, 0, 1, 0, 1, 0, 1, 0. So that tells me D sub B is equal to B prime. So that gives me, an opportunity to provide an instantaneous implementation by inspection. The other one, which is 0, the other bit, 0, 0, 1, 1, 0, 0, 1, 1, well, that's equal to A. So D sub A equals A. So with my D flip-flop, being the way it is, I wonder if I've overstated it. 0, oh no, it's this one. I went to the wrong one. It should be 0110. 0110. Shoot, I wrote down the wrong line. I wrote down A instead of A+. And this should be 1001. Sorry about that. 1001. So if that's the case, then it seems to me like what we really want to do is write another K-map. Sorry about that. So that'll be B. 0, 1, 2, 3, 4, 5, 6, and 7. And then 0, 1, 1, 0, and 1, 0, 0, 1. Well, that is an exclusive OR. So what we'll do is we'll have to loop everything. Pain in the ass. Sorry about that. But that's what exclusive OR does. This is a 3-input exclusive OR gate. So what we'll do, let's switch back, let's change colors, is U, A, B. And then this is going to be B prime. So that'll be the up-down counter input. Here comes A and B. And you can write this out as 1, 2, 3, 4 different AND gates feeding into a single OR gate if you like, or you can take the shortcut of writing the exclusive OR, because there's no good way to do a minimal form here. You're going to end up with essentially a separate product term for each loop. So the material change, right? I mean, this is kind of a big material change. We've gone from a 2-input exclusive OR to a 3-input exclusive OR when we went from toggle to D. So that's kind of cool. So you can see the implementation changed materially. Let's do another example here. Question number 16. A bipolar junction transistor gets its name because both electron and hole charge carriers are used, and in contrast, unipolar transistors such as field effect transistors use only one kind of charge carrier. If you have any questions about that, you can use the Google, but the answer is true. A bipolar junction transistor, also known as a BJT, and drawn schematically in this way, that's a BJT. You call this the base. You have a collector and an emitter. This is a either a switch or an amplifier. To run it as a switch, what you do is you use current that's sufficient to drive it immediately to the upper supply rail. So if this is 5 volts and this is 0, you want an input current sufficient so that you can go straight to the upper supply rail. If what you want to do is run it as an amplifier, then what you need to do is make sure your current input into the system stays within the linear mode. That's the current into the base. So that's a if you run too much current into the base, it goes into saturation and hits the supply rail, which may be what you want if you want it to run as a digital switch. But if what you're really looking to do is make this to an amplifier, you want to lower the current and keep it in the so-called linear range. And then you'll have a nice linear amplifier. So that's that. Let's get another sheet of paper here. So, one of these says, how many ways can we implement a flip-flop X using flip-flop Y when X is coming from the set of flip-flops that's equal to SR, T, JK, and D, and Y comes from the set of flip-flops SR, K, JK, and D. So how many different ways are there to implement one flip-flop with another? Any ideas? Bridget, what do you think? No, it's not infinite. We made a matrix last time. I'm sorry, could you say it again? Is it drone? Oh yeah, 12. Yes, it's 12. That's correct. And so we get that by going SR, T, J, K, and D. Right? And so when we look at the matrix, SR, T, J, K, and D, right? What we see is, well, we don't implement an SR with an SR. So we take out the main diagonal, and what we're left with out of the 16 different combinations, you could say I'm using, or I'm implementing using, I think that's how we did it last time, implementing using, right? So I implemented D using an SR, implemented D using T, implemented D using JK, but I don't implement the D with a D because I already have the D. So there's 12 different ways, because we took out the main diagonal, of implementing flip-flop X with flip-flop Y. Let's see, question 18 asks about an interesting switch. This is called a reed switch, and it's encased in a piece of evacuated glass, and what you do is you bring a magnet nearby, and the magnet causes the switch to close. And so what I'll do is I'll just draw a little bar magnet with north and south. You bring that nearby, and the magnetic field goes through the steel switch and causes the two switch pieces to close. And this is very useful if you have something like a burglar alarm and the magnet is on the window. When the window is open, this shifts out of the way, the alarm goes off because it senses that this is normally open, and when this was closed, you can do it a couple of ways. You can have a normally open switch, or you can have a normally closed switch. When it's in proximity, you can make it so that it opens, and then when you open the window, this thing closes, and that causes an alarm to go off, if you like. That's very useful also if you're in a flammable atmosphere. And this was invented in 1936 by a fellow named Walter B. Elwood at Bell Labs. So that's an interesting idea. Switches that operate in without any contact. It's a non-contact operational switch, and they put an inert gas inside so you don't get corrosion if there's a spark generated when the switch closes. so you don't erode the switch contacts. So that's kind of cool. Let's see now. So that's called a reed switch. Any other questions about homework 8? Number 8. Assuming zero setup and hold times, clock latches and flip-flops produce the same outputs as long as the inputs do not change while the clock is asserted. So in other words, if you have a stable input, right? So here's D. Now, if the clock pops up and then pops down, and then D is only sampled when the clock is asserted high, then it doesn't matter if you have a latch or a master-slave edge-triggered flip-flop, it'll produce the same output. But if you said, well, I'm only going to trigger on the rising edge, then I'd say, well, okay, that makes it, somewhat more safe in theory, but if you know the input is going to be stable during the entire clock pulse's duration, you don't even have to bother with that. And so you can use a normal if you like, flip-flop. And so in theory, all you'd need for a D flip-flop might be something like this. And you could do it as a D latch, or if you want to clock it, you could do it like that. And when the clock comes in and it's high, D goes through, and you get a nice little D flip-flop in there. And so that's a clocked D flip-flop latch, but it's not edge-triggered. So assuming zero setup times and hold times, clock latches and flip-flops produce the same outputs as long as the inputs do not change while the clock is asserted. So while the clock's asserted, you don't want the inputs changing, and that's true. They'll work the same. I got a little time left. You want to try another one? Homework 8? Okay then. It's an awful nice day out. It's a little windy and chilly, but not bad. Enjoy the rest of the day. Please don't forget to submit your midterms. Blackboard will be brutal about late submissions. It won't permit them. And it sounds like you guys have already submitted your stuff because you didn't have any questions. So good luck to you with the midterm, and enjoy the rest of the day, and thank you for your attention. Thank you.